This lecture is going to cover chemistry as well as properties of water. To begin with, we're going to talk about bonding. Bonding occurs between atoms in order to go ahead and allow them to bond to one another, and these will bond in ways that create more complex molecules. We'll be dealing with really simple ions, like the hydrogen ion in this class, which is simply a hydrogen atom without its electron. So it's missing this outer negatively charged electron, and it's just a positive proton. So we'll be dealing with that, and then we're going to be dealing with huge macromolecules that we're going to call polymers, like big proteins and big complex carbohydrates. Okay, so the bonding that you're going to need to know about is covalent bonding as well as hydrogen bonding. And in this example, it shows you a covalent bond. So this is showing two hydrogen atoms that are combining to form hydrogen gas. And with covalent bonding, this is a strong bond, and the electrons are shared between both of them. If you've had chemistry in the past, maybe you remember something called valence. And so valence is met here. If you haven't had that before, no worries. These electrons are shared though, and in the process of sharing those, they stick together, basically, and form a really strong bond. You can see this as well with oxygen gas. So oxygen and oxygen sharing multiple electrons between the two of them. Okay, so this is considered a non-polar covalent bond. Non-polar. And the reason it's considered non-polar, both hydrogen gas as well as oxygen gas, is that there's no net charge on the molecule. So when these combine, it's neutral, and there's no, positive, and there's no negative, net positive or net negative. I know you see plus signs and minus signs here, but they cancel each other out. That is different for a second type of covalent bond, and this is a polar covalent bond. And a good example of this is water, because we're going to be talking about water in just a moment. Here's your water molecule. You've got oxygen, and you have a hydrogen and another hydrogen. And usually when you write this molecule, you write it like that, right? And you don't show these pluses or minuses, but in all actuality, there are pluses and minuses on a water molecule. You might be surprised to know. It's just that they're not full-blown charges, and so you don't get to write it out like this. These are actually partially positive, that hydrogen is, and this hydrogen is partially positive, and this is a partially negative. Okay, is the oxygen. So here's why. In polar covalent bonding, you have an unequal sharing of electrons. So essentially what you're going to need to remember for this class is that oxygen and nitrogen are the greedy elements, because when they bond with the hydrogen, what happens is they like to steal the electron for a lot of the time. Not the whole time, just part of the time. And since it's still sharing that's going on, it's still considered covalent. Now, if nitrogen were to snatch that hydrogen's electron permanently, that would be an ionic bond. Okay, so a little bit of a difference there. So this is covalent bonding. There's sharing going on here, and you have a partial negative and partial positives. So here's what that looks like. Oxygen and hydrogen. Obviously, oxygen's electrons are being shared with hydrogen, and hydrogen's one electron is being shared with oxygen. But because there's so many more protons for oxygen with that positive charge, remember that in chemistry, opposites attract. And so the electrons tend to be near oxygen more often. So the electrons hang out near oxygen more often, and the charge on an electron is negative, hence the partially negative. Okay, so partially negative because the electrons hang out near the oxygen more often. So that explains the negative charge on oxygen, partial negative. Why are these positive? These are partially positive because when all the electrons leave, all it's left with is its single proton. and that's why it's partially positive. So what you need to know is that water engages in a polar covalent bond. And anytime actually you see O to H or N to H on a molecule, you'll know that there are charges, okay? There are some partial charges going on, and you know that molecule is going to be polar, which will be really important when we start talking about nutrition. So let's go back a slide. Nonpolar, no charge, equal sharing of electrons. Polar, charged, unequal sharing of electrons. Okay, so that's nonpolar and polar covalent bonds. All right, let's go ahead and talk about water for a minute. Water is considered the universal solvent in biological systems, and that is because it is basically, if you will, the bathtub that everything gets put into. So in this instance, you can see salt being put into a water-based solution, something like a soup. And that happens in cells too. So cells are mostly composed of water. They're about 85% water. And so everything is going to get dissolved into that water. So in living things that are mostly composed of water, water is the universal solvent. Now that matters because the stuff that's going into the water is called the solute. Okay, so water is always going to be the solvent. The solute is always going to be what you put into the water. In this instant, salt. And this matters. See, look at these. Salt, sodium, and chloride. Now, if we take those here and we see what exactly will water do when it encounters a sodium ion or a chloride ion, what it will do is it'll form something called a sphere of hydration. All the water molecules, all the little plus signs, are going to match up with that minus sign. Right? So you can see that how they are oriented towards the chloride ion. And in that way, they're going to be able to break apart something like a salt crystal. Water is going to come in there and it's going to form spheres of hydration around individual ions. Now notice here, it's the negative sides that are oriented towards the sodium ion. And so water is a universal solvent. It is able to actually break things down. So that's going to be important in nutrition as well, as we talk about these polymers that we eat that need to get broken down before they come across the gut and into the blood. Now, water can only break down polar molecules. So it has to be polar in order to be soluble, right? So if something's soluble, water is actually able to break it down. Okay, and so what you're going to need to determine is, well, what molecules are polar and which ones are nonpolar? Well, so far what you know is that in order for something to be polar, you have to have an oxygen to hydrogen or a nitrogen to hydrogen, because that's a polar covalent bond where you have unequal sharing. So you could look for those combinations on the molecule. Or you could have full-blown charges. Look at these ions. So ions are salts with full-blown charges. They are very, very polar. So you could also just look for plus signs or minus signs on the molecule that indicate charge. And if you see any of these, 1, 2, or 3, then what that means is it's polar and it's soluble. Water is able to break it down. Now, not everything is soluble, right? So some things are not soluble at all. You know this because you have worked with fats in cooking. So something like olive oil, which is made up of triglycerides, that is nonpolar because there are no polar regions on the molecule, and you can see that water-based vinegar completely separates from that. So there are nonpolar substances inside of our bodies and that we consume that go into the blood, and we're going to have to talk about how those move around in the body. So a big one for us here are fats that are nonpolar. So not everything is soluble that you're going to see, but a lot of things are, or they have polar sites on them so that water can attach. Okay, that concludes your introductory chemistry lecture.